Ampetronic. Listen to the difference.
Hi, I'm James from Ampetronic, and I'm here to present a session we've entitled What to Do If My Hearing Loop Doesn't Work Well. Hearing loop systems have, at times, gained a reputation as a mysterious, unseen technology, but there's no magic involved. Our intention today is to demystify the technology by discussing techniques for measuring system performance, highlighting common performance issues, and outlining how we can address those. The first step in improving the performance of our hearing loop is to gain a clear idea of exactly where we are in terms of system performance.
It might be that we've received some user complaints, somebody saying the system doesn't work at all, or people are struggling still to hear, even though they can hear something through the system. It might be that we haven't received any complaints, but there is a bit of an element of doubt about how well the system is working.
Or it might be that the power light's on the amplifier, there's some lights flashing, and so we assume it's got to be working. And that was certainly my position before I started working for Ampetronic, so it's entirely understandable. But there is a bit more to it than that, as we'll see in a short while. It might be that we've taken some measurements with a calibrated meter. It may be that those are not so good, and we know that we have got some performance issues that need to be rectified. Or we might be basking in the smug satisfaction of knowing that our system is working really well because we've got some standard compliant readings to report, possibly somewhere in between those two. Our previous site survey work that approximately 50% of systems that we come across installed there out in the wild are essentially entirely non-functional, whether that's through failure or extremely poor performance. And only about 5% of systems are standard compliant. So there's, generally speaking, quite a bit of work to be done by the average system owner. The most important thing is that we get objective data to show us numerically where the system performance is. If we rely on either end users and their hearing aids or on our own ears using a loop receiver, that can cause some problems for us. It may be that either we can't get hold of a hearing aid user, or it's really not appropriate to be grabbing them and saying, we need you to help us with this. It might just not be the right environment for that kind of interaction. And whether it's our own ears or the ears of a hearing aid user, the results may not be entirely reliable. It's a bit of a tricky subject, this, because clearly the proof of the pudding with any kind of assistive listening system is in the eating. If the users benefit from it, then that is good. But we find two problems here. First of all, that our own ear-brain system is very good at getting the best out of imperfect audio. So we can find, if we as people with good hearing are listening to a system, that we're getting a false impression of how good, bad or ugly the audio performance might be. And the issue which we often run into with end users is that because such a high proportion of loop systems don't work as well as they should do, the benchmark for what good sounds like is really askew of where it should be. So people may well be listening to something which is as good as they're expecting it to be, but it could be a whole lot better. And it's not unheard of for people who've been using loop systems for a couple of decades to, for the first time, hear a system which really works properly and be astounded by how much better it sounds than what they're used to. So it's perhaps a little bit dangerous for us to say we can't rely on hearing aid users when clearly they are the ultimate users of the system, but actually through the failures of poor system performance that we see out there, they can have an artificially low benchmark for how good the systems should be. So how do we go about getting those objective readings that we're really looking for? Well, we ought to use a calibrated meter, and there's various different products on the market. We saw the self-contained field strength meter on the previous page. Here we can see our Apple iOS-based software-driven meter, Loopworks Measure. This uses a small hardware interface to turn our Apple mobile device into a very powerful loop field meter. But all these devices fundamentally do the same job, and there are three core measurements from which all of the other tests that we have to do are derived. And those are measuring magnetic background noise, that is the not acoustic background noise, but magnetic noise generated by mains wiring and plant equipment that might represent itself as a buzz or a hum to a user, something that we really don't want to be hearing. Then we've got the strength of the signal that we are generating, effectively the volume level that a user receives. And finally, the system frequency response. And unfortunately, the things that go wrong there often impact clarity, intelligibility, and all the things that really we desperately need in a system of this nature.
At this point, we might have identified some aspects of system performance which are not quite where we'd like them to be. Let's look at why that might be and what we can do to address those issues.
So the first problem area we want to look at is high background noise, high magnetic background noise. We quite often have people phoning us up saying, I've got too much mains hum. And usually that actually isn't the case. In this scenario, we've clearly got a signal to noise ratio issue. People are listening to their wanted signal and there is excessive noise. But whenever you've got a signal to noise ratio problem, it can be that you have insufficient signal. It can be that you've got too much noise. When it comes to loop problems, it is normally the former rather than the latter. And if we get a numeric reading of the background noise level, it very often proves to be adequately low. The problem we've got is that the field strength is also far too low. So a user who's got a receiver with headphones is perhaps turning the volume on that device up to compensate for a low field strength. They turn it up until the signal's loud enough, but by turning the volume up, they've also amplified the background noise. So that can be a little misleading in terms of what's actually going on there. In a very small number of cases, we can genuinely have excessive magnetic background noise. The majority of that will come from mains wiring and plant equipment. So it could be that we've got either wiring faults or bad wiring practices if we're looking at old electrical installations. One example of a bad wiring practice we occasionally bump into is seeing where particularly lighting circuits have been wired in singles with the live and neutral split around the room. And once upon a time that was permissible, but it was outlawed quite a few decades ago in the wiring regulations. But if we are dealing with an older building with an older electrical installation, it's possible that we will see that. And by having the live and neutral split as they move around the room, we effectively have a 50 Hz mains induction loop being formed, and that generates very high background noise levels in the room. And really the lighting circuit just needs to be updated so that it's in line with current wiring regulations in that case. Far more common is to find that we've got some kind of heavy plant equipment nearby, so that might be ventilation, air conditioning type equipment, plant associated with lifts, elevators, etc. Or probably the most common of all, if we have the main step-down transformer from the transmission lines that is providing the main supply for our building, or possibly the surrounding buildings as well, typically down from 11 kilovolts to the 230 415 volts that we're normally dealing with within a building. And a large transformer generates quite a large magnetic field. So if we have one of those through the wall in a plant room from where we're sitting, we may find ourselves with a localized background noise problem. The transmission lines themselves can also cause that sort of problem, but I think it's worth putting this in perspective. I've probably measured thousands of systems over the years, and I can probably count on the fingers of two hands the number of rooms where we run into this kind of problem to the point where a system really couldn't be installed. So it's a very rare occurrence. The most common form of background noise is actually not mains hum at all, but overspill from other systems nearby. So that is something to be aware of. If you're putting a new system in and you've got an older system in the room next door, we may well find overspill from that space, and we'll cover that in more detail a bit later. We can also have a problem, the other side of the signal to noise ratio issue, with low magnetic field strength, and this is really far more common. Field strength is proportional to the current that's flowing in the loop. So essentially, if we have a low field strength, we just don't have enough current. That can be because the amplifier is insufficiently powerful for the scenario we're dealing with. We're assuming for the moment that we've turned it all the way up. So if we've got it running flat out and we're still low on field strength, our amplifier is insufficiently powerful. We can end up needing a disproportionate amount of power if we're seeing signal losses caused by metalwork in the building structure. And we're going to hear a bit more about metalwork shortly, so we'll gloss over that just right now, but it's worth being aware that is a potential cause of low magnetic field strength. When it comes to specifying products, historically our industry has worked on the square meterage the amplifiers will cover. The problem with that is it's really not all that reliable. You can see in a couple of scenarios here, both 240 square meters, but we're 2 models apart depending on the shape of that room. And that's simply a matter of distance from the nearest loop conductor to the user. You're really not going to be more than 2.5 meters away from a wire in the corridor type scenario there. You're nearly 8 meters away in the square room. So we need more power where we see a square room. The danger is this makes it quite easy to make amplifiers look more capable than they are. So we would just really encourage you to not pay too much attention to the square meterage figures and look at a more rounded way of specifying products, which we'll come back to a little bit later. So as well as the field strength being wrong at a given point in the room, we've also got to consider how consistent that field strength is across the room. It's no good having dead spots and areas that are better and worse. We really want the greatest consistency possible. And there are 2 primary reasons why we might see poor field distribution across our room. One is if the loop geometry really is not what it ought to be. And by that we really mean the relationship between the size of the loop and the installation height. Generally speaking, up to about 15 meters in the narrower dimension, you're absolutely fine at floor level, and we will tend to specify systems at floor level by default. But if we are looking at much larger loops, let's say we're talking about a big church or a cathedral, we're very likely to have to elevate that loop in order to get the field adequately consistent across the space. The practical side of this really is to use a modelling tool to help us design that system, or indeed to consult an expert who can help us with it. We're going to touch on support and system modelling a little bit later. The secondary factor is that if we do have significant amounts of structural metalwork in the building, as we mentioned a minute ago, as well as affecting the field strength at a given point in the room, it can also increase variation across the room. And that's really what we're seeing with this illustration over on the right hand side here, that the further we get away from the loop around the edge of the room, it's good signal around the edge of the room, the further we get into the middle, the poorer the performance becomes. And it's effectively because the metalwork has a greater opportunity to attack the signal, if you like, the further we get away from the loop. We'll come back to how we deal with that in a separate section on metalwork in a short while. And the final one of the sort of fundamental issues, if you like, is to look at system frequency response. And here we see an example result from the spectrum analyzer mode of Loopworks measure, showing us a quite significant high frequency roll-off. There's 2 main reasons we see this sort of performance. One is that we're simply not dealing with a very well designed product. Loop amplifiers have got quite a tough job to do in a number of ways. They drive very low impedance loads. The thermal demands we make on the amplifier are quite significant. Loudspeaker amps generally only go down to about 2 ohms. Loop amps very often go down to 0.2 of an ohm. So we make demands there. But also the impedance curve, as it varies with frequency, it varies far more extremely than the impedance of a loudspeaker will. And that can in itself result in a very poor frequency response. You need to have a well-designed amplifier to cope with this tough job that we're asking it to do. And quite simply, a fair number of the products on the market do not give us a good frequency response by design. And the solution to that really is to make sure you use a quality loop product. And I can't imagine where we could possibly get one of those from. The secondary issue is something we've already covered a couple of times, metal losses. You'll see this subject coming up over and over again. And that's really irrespective of the quality of the product. It has nothing to do with that. We could take that same system and put it in a non-metal environment and it would work perfectly, shift it into a room where there's a load of metalwork and suddenly we have a problem on our hands. The solution there is to make sure we have the right type of system specified, and again, we're going to come back to that shortly. And then when we've got our system spec right, make sure the system is correctly commissioned. There are some adjustments we can make to optimize the frequency response. We must make sure that we do that. Okay, so as we hinted a couple of times a minute ago, we were going to come back to look at the subject of metal loss in more detail. As we've just seen, metal structures in the room we're working in can cause signal losses in terms of field strength at a given point in the room, excessive variation in field strength, and by affecting the frequency response. And again, the frequency response can vary across the room. So both the field strength effects and frequency response effects are really not good news from a signal to noise ratio and intelligibility point of view. Just a piece of metalwork is not necessarily a problem. It has to appear in a certain form, generally something which is in the same orientation as the loop, so horizontally orientated normally. Something which is quite physically large compared with the loop, so covering most of the floor, and that forms a grid or sheet structure. So typical problem materials include reinforced concrete, steel mesh reinforced concrete, aluminium grids to support suspended ceiling tiles, and profiled steel deck construction in modern buildings. They might be thinking, but I've got a traditional construction stone and timber church. I really don't need to worry about this. That may well be the case, and in fairness, the house of worship sector gets off more lightly than the average application area might, owing to the nature of many of the buildings. But there's two things to consider. Obviously, a lot of congregations are now meeting in more contemporary buildings, and really anything built after the middle of the last century, we cannot assume that there is not significant metalwork in that structure. And even in traditional buildings, sometimes if we've had an uneven or unstable floor, the flagstones may have been lifted, a concrete slab poured, and the stones put back down again. So it might be worth just consulting anyone who's been around a long time to make sure that no work like that has ever taken place, or if in doubt, maybe have a little waft around with a metal detector if you can borrow one. And if you're finding metalwork showing absolutely everywhere you go, then it's an indication there might be something that requires some further investigation. But generally speaking, this is a problem mainly associated with modern buildings. So what can we do about this? I mean, the issue we saw a minute ago with the sort of black hole in the middle of the room, that is the typical behaviour associated with a perimeter loop installed in a room with metalwork present, where the loop is too big for that to be a safe approach. If we put a perimeter loop into a really small room with metalwork present, we'll normally get away with it, provided we add enough amplifier power. But the bigger we make the room, the riskier and riskier that becomes, and we start to see that black hole effect emerging, which we saw earlier. So the solution here is, instead of having one big loop, we install instead several smaller ones. And here we see an array of 5 smaller loops. Each of those would be perhaps 3 meters wide in the narrower dimension. We put as many as we need in to fill the room up, and then over the top of each of those, in this case 5 individual loops, we would get good performance, irrespective of any metalwork present. But in the gaps in between, we're going to get dead spots formed. So it may be that there are aisles and that kind of thing we can hide those dead spots in, but in many situations that's not going to be acceptable. So to get around that problem, we simply install a second set of loops overlapping the first set, and the green and red circuits simply fill in the gaps in each other's coverage. Together those form what we call a multi-loop system, and the clue's in the name. It means we've got multiple loops instead of one big one. You can see we've got a red circuit and a green circuit there. Each of those requires its own amplifier channel, and so we have special products with two outputs to drive those two circuits. But with all of that done and correctly commissioned, what we find is instead of that black hole effect we saw a minute ago on the previous slide, we now have smooth, even coverage all the way across the room, irrespective of the influence of structural metalwork. Another issue that we should be aware of is that of overspill. If we look at a traditional perimeter loop, a single loop around the edge of the room, that will spill its signal significantly outside of the room. You can see that illustrated just here. Now that's probably best known in the wider application areas for being a problem if we have adjacent spaces. And if we've got multiple rooms that we're concerned with within our building, then we should be aware of that. You're looking at overspill extending at least one whole width of the room away. And often it can be multiple room widths away. So it can be quite a substantial problem. Probably the bigger issue actually in many church environments is electric guitar pickups, magnetic pickups of course they are, picking up the loop signal. And that can cause a distraction to guitarists if they're hearing our front of house mix coming out of their guitar amp. That can be pretty distracting. But it can also cause feedback if we are then feeding that guitar amp output into our front of house PA, which in turn is being fed to the loop. So you get a feedback path. We tend to associate feedback with the acoustic domain. It can also occur, of course, in the magnetic domain. So we need to be aware of that. We can control this overspill effect. So the way we do this is actually quite similar to what we just saw with the loss control type systems. So again, we have multiple narrow loops instead of one big one. But you'll notice this time the loops are of different sizes, and that is key to making this work properly. We need a really specific design tailored to the space in question to get this to work properly. And with this arrangement of loops, we will see overspill control outside of the room. However, as in the previous example, in between those individual loops we'll get dead spots. So as before, we put a second set of loops in to fill in the gaps. And together those provide us with even coverage outside of the room, but a really nice sharp drop off outside of the room. Now in this example we're looking at two spaces that are intended to be used side by side and we don't want any crosstalk, but it would be easy to say turn this through 90 degrees and imagine that our worship group is to the right hand side of the view here, and we've avoided there being a significant amount of magnetic field being presented to those guitar pickups. So a couple of different ways in which low spill can be useful to us. Now moving away from the wireless transmission side of the system, it's perhaps worth taking a step back and thinking about what assistive listening systems are there to do in the wider sense. There still can be a perception that there's some kind of magic going on inside the loop amplifier, or something to do with it being a magnetic system is what helps users. The reason we use this rather unusual technology is nothing at all to do with magic properties of the signal transmission path. That's convention that dates back to the T setting on the hearing aid being introduced to help people speak on the telephone. It was to couple to a telephone earpiece. The improvement in audio quality for a user is all about where the signal is derived from. So instead of using the inbuilt microphone in the hearing aid, we then have the freedom to place a probably directional microphone as close as we can get it to the person or people who are talking. So there's the opportunity, as we've just seen, for us to make a mess of the wireless transmission portion of the system. But actually the biggest opportunity we have to get it wrong is to get the inputs wrong. And exactly the same audio principle applies here as to almost every other field of audio: garbage in, garbage out. So the quality of the microphones and their placement and the type of microphones we've selected is really important when it comes to getting our system performance right. Normally, the ideal scenario will be to give every person talking a lapel or headband radio mic. It's all about shortening the acoustic path from talker to microphone, and that really is about as short an acoustic path as you can possibly get. Conversely, the worst possible scenario, which we do see quite often, is the omnidirectional boundary microphone in the middle of a ceiling. You couldn't really get the microphone much further away in many cases, or have a less discerning pickup pattern on the microphone. And you can probably imagine how accurate and near field the sound from that type of microphone is. Of course, there's a need for compromise in many situations, and it may be we've got a budgetary limitation, a practical or aesthetic limitation, which is in conflict with what would be ideal from an audio performance point of view. But I think the key concept here, or two key concepts, one is that we've got to improve on the quality of what the hearing aid microphone in isolation would do. That is the absolute minimum requirement placed on us. What we're really aiming for is to get the microphone as close as possible to the talker to minimise that acoustic path, and to remember that really if we wouldn't take this microphone approach for any other purpose, be that recording or sound reinforcement or whatever it might be, we shouldn't do it for assistive listening. There's no magic in the loop amp that will de-reverberate the signal that we're putting into it.
It may, however, be that a hearing loop is not the most suitable solution for your particular environment.
There are 4 common assistive listening technologies that we should be aware of: induction or hearing loop, infrared, radio, be that FM, analog or digital, and audio over Wi-Fi. We're going to have a look at those grouped up by their operational mode now. So the first thing to look at are the receiver-based technologies, and that's infrared and the radio systems. The key benefit here is that they're easy to install, and that's particularly important in an architecturally sensitive or retrofit environment. Essentially, we just have to fit an antenna or an infrared radiator or series of antennas and radiators to the wall, and our installation is complete. So that side of it is very easy. But the downside is that we have got to deal with receivers, and that's bad from a user point of view because they have to go and ask for a device on arrival, and they've got to wear that device. And some of them are more elegant than others, but none of them are necessarily the most user-friendly of experiences. Some of them are downright unpleasant. Conversely, the venue has to buy those devices in the first place, which can be a considerable cost, and then administer them. So there is an ongoing burden on the venue associated with making this provision. Moving on to the loop side of things, this is almost the polar opposite. It's a bring your own device solution. So the user turns up with their own receiver in the form of the hearing aid. We talked about the telecoil and how it was originally developed for use with telephone handsets. The vast majority of hearing aids dispensed in the UK have a T setting, and hopefully the user is familiar with using that mode. So all they have to do is walk into the venue, see that from the signage that there's a system in place, flick the switch on their device, and they're in business. No need for any interaction with staff at the venue or to wear anything which singles them out as having a difficulty with their hearing. So from an experience point of view, not having to deal with receivers is the big benefit. But we've actually got exactly the opposite negative side of things, which is that whereas the receiver-based systems have an easy installation, generally speaking, loop systems will be harder to install. So we tend to view this as short-term pain for a long-term gain, that it's worth the awkwardness of installing loops. But we do acknowledge there may be some circumstances where it just isn't possible, whether that's for architectural or practical reasons. It can also be in some scenarios that we need to install a particular type of system, say a multi-loop, and that's just not going to be viable in terms of having access to underneath floor coverings and that kind of thing. So that's where we run out of luck with loop, but this is always our preference where we can install it. And finally, we've got a secondary bring your own device technology to look at in the form of audio over Wi-Fi. Relatively recent development. It's quite an interesting topic. It looks very attractive at a glance. The more you get into it, the more some complications start to appear. I think it's fair to say it is easy and convenient and attractive for tech-savvy users. If your congregation are likely to be people who own smartphones and are comfortable with using them, then this works really nicely in that sort of environment. The other side of that is that if your congregation does not have that many people who are tech savvy or are going to have a smartphone, etc., present, then it makes life much more difficult, and then people are far more likely to struggle with getting themselves up and running in that environment. So I think the success of these systems is quite environment specific, if you like. And there can be some further difficulties associated with the technicalities that if we are having to work with a communal Wi-Fi system, I know some congregations meet in sports centres and the like, where they're using shared facilities. Actually getting that up and running may not be particularly trivial. So there's a real scale of how easy it is to get the IT side of this sorted out, depending on the circumstances. And we do have to consider that there can be considerable latency in the system. If we are talking about relatively small rooms where we do not have a significant acoustic propagation delay to consider, and we have good line of sight to the talker, can be quite disruptive if we're trying to, if we're seeing bad synchronization between the received audio and what we might be partially lip reading. So there are some technical issues to consider along the way as well, but certainly an interesting technology to look at. It's worth briefly mentioning we are relatively agnostic when it comes to which technology we look at. We can supply all of these systems, so we're not favouring one over the other because we can or cannot supply any of them. We just think the balance of benefit still at the moment lies with Loop. A final thought on this, a survey was done a few years ago for the Audio Engineering Society, part of their look at assistive listening technologies. A group of people were asked to express a preference for Loop versus a receiver-based technology. As you can see, the vast majority of people favoured using Loop over the receiver-based technologies. As you may have noticed, this predates the common availability of Wi-Fi systems. They were not included in this survey. I did see a similar survey more recently, which suggested that around about 25% of users would prefer a Wi-Fi solution. I don't know if that was conceptually or having actually used one, but informally we have that as an interim result, but still the majority would prefer a Loop solution. If you want further assistance with any technical problems or specifying systems, we have a sizable tech support and system design team. You can get some guidance from our website, and there's also a live chat feature on the website where you can talk to the engineering team. Or more conventionally, you can email or call in to get that assistance. Quite often in the church environment, we're looking at a self-installation scenario, but it might be you're looking to get someone to install the system for you. We have a network of installation partners. We could put you in touch with somebody in your part of the world who we work with regularly. On the subject of support, we touched on it earlier, that when choosing a system type and designing a system, really we need to look at something more advanced than square meterage. We need to use a modelling tool. Our product here is Loopworks design. You put in some basic parameters about the scenario, the length and width of the room, the installation height if it isn't going to be floor level, the metal content and whether we need to control overspill, and you will get out some graphics that will illustrate the expected performance as well as a hardware specification, what product we should look at. So this is sort of the replacement for looking at square meterage, essentially. So if you'd like any further information, we're doing a brief question and answer session just now, so please ask away. Equally, if you think of any questions later or you want any further information, please do give us a call or visit our website, www.ampertronic.com.
Thanks for your time.
Amplitronic. Listen to the difference.